So James, should I get? Good afternoon. I hope you had a lovely lunch, and I'm very glad to see you here. Following this first plenary discussion, it'll be focusing on mountain cryosphere and groundwater. This first plenary is moderated by Dr. James Thornton. He's from the Mountain Research Initiative of the University of Bern in Switzerland, and there will be two input presentations, one by Dr. Tobias Jonas from the VSL Institute for Snow and Avalanche Research in Davos, Switzerland, as well as from Professor Lauren Somers, Dalhousie University, Halifax, Canada. James will introduce all the details to the QR code and will also now begin this panel discussion. Thank you, James.
Thank you very much indeed, Philip. Good afternoon, colleagues and friends, and a very warm welcome from my side to this first plenary session of the Congress. As Philip mentioned, I work in the Coordination Office of the Mountain Research Initiative, which is a large international network of researchers working across a wide range of topics around the world's mountains. And the topic today, mountain cryosphere and groundwater, is extremely pertinent, not only given the mountainous setting in which we meet, but also the time in which we meet. The world's mountains are warming extremely rapidly, in many cases faster than the adjacent lowland regions. And this, of course, has profound consequences for glaciers, for snowpacks, and for permafrost. For example, here in Switzerland, during the last two summers, 2022 and 2023, we lost 10% of the national ice volume, which is a really incredible amount in such a short period of time. However, due to the difficulties associated with monitoring and characterizing mountain hydrogeological systems, even our present-day understanding of these systems and the implications of this cryospheric change are still rather unknown and remain very limited, even in such a data-rich country as Switzerland. And accordingly, the spirit of this session is very much to encourage and to explore possibilities for collaboration, more extensive collaboration indeed, between cryospheric scientists on the one hand and hydrogeologists on the other, in order to unravel the effects of these changes on mountain groundwater, which, as we heard this morning, has extremely high societal relevance and also relevance for ecosystems, not only in our mountains, but also in the connected lowland regions in which many of you surely live and work. So during the first part of the session, we will have two short input presentations from Lauren and Tobias. Actually, Tobias will speak first. Tobias is group leader, as Philip already mentioned, at the Swiss Federal Institute for Snow and Avalanche Research, the SLF, based here in Davos. So surely, Tobias, you win the prize for sustainability in having the lowest carbon footprint to travel to attend the conference. And the second presentation, after Tobias has spoken around his area of expertise, which is mountain snow dynamics, will be Lauren. And Lauren is at the forefront of the rapidly growing field of mountain hydrogeology. She's also one of the key people making extensive efforts to reach out to other disciplines and to foster this collaboration, which is so very much required. So we're extremely grateful also, Lauren, that you could make the slightly longer journey to be with us this week. Following these presentations, we'll have a short moderated discussion to debate the topics from different perspectives, as well as the interface, the interaction between these two disciplines. And in the final segment, if time allows, it will be over to you, the audience, to pose your questions to our expert speakers. Since you are very numerous, we won't do this in the traditional way of passing a microphone around, but rather the QR code, which you see on the screen in the top right here, you can scan it with your smartphone, and you can submit your questions via this system. Questions can be asked at any time, so please, if a question pops into your mind, please do submit it. And also at the end of the session, we will also encourage you to share any more general feedback which you have related to what you've heard or ideas for future work. So with that, I would like to immediately hand over, please, to Tobias. Thank you.
Yeah, thanks, James. And it's an honor to speak to you here as a local snow researcher. My institute is just 1 kilometer away, so speaking of carbon footprint, I could have walked. I took the bus because I like snow more than rain, and it was raining when I left home, unfortunately, so I apologize for that. So I hope I'm able to give some input to the discussion, so some general considerations, which I'll present in the next 15 or so minutes. So I am looking into how to assess snow water resources and surface water inputs in such a setting that's illustrated in this picture here. So the logo of the conference has 3 mountains, so I depicted something similar. It's actually a picture from Davos. You see the valley in the center is the Dishma Valley, which is probably known to hydrologist researchers, I would guess. And that's the topics I'm going to cover in the next few minutes. So I would want to discuss a little bit modeling strategies to assess snow water equivalency, surface water input, and similar variables that should be of interest. I would also look into supporting data sources and how we could possibly integrate them into these assessments. We shall discuss assessing past and predicting future snowmelt. And finally, I have one slide on the interfacing between snow models and hydrological models with more questions than answers, so to spark some discussion at the end. So that's a very general overview about strategies and modeling strategies to assess snow water equivalent, not for a single point, but on a catchment basis. So we are talking about gridded assessments so that we have some spatial resolution of whatsoever, whether it's lumped or fully distributed. And it all comes down to 3 important points. The one thing is you need some sort of meteorological forcing. And it can be anything from just precipitation and air temperature for temperature index models to a large list of meteorological variables, such as the ones that are listed here, which are typically needed for more physically based assessments. And they can come from numerical weather prediction models, which is typically used in operational settings, or from reanalysis data sets typically used in simulations for past time or regional climate models where you can cover past and future conditions. And normally those models that provide forcing data, if you're not looking at station and single point, but at grid data sets, they come at larger spatial resolution than we would want for snow model assessment, because snow model snow cover is variable in space and time, and the variability happens at small spatial scales. So just running a snow model at 5 kilometer scale is kind of pointless here in the mountains where the topography is so complex. So you will need some methods to downscale this input data, post-processing, possibly debiasing, depending on the settings and of the input data sets, obviously. And if you have done that, you can run a snow model. And again, depending on the data you have available or at hand, you can run a physically based, a conceptual model, something hybrid in between. And you need to consider different land surface types, such as open landscapes, such as forest, glacier surfaces, urban settings, depending on whether or not you're interested at these elevations. And then you can use data assimilation to incorporate observations of some sort. That's possible, obviously, only for now or the past. No data assimilation to work in the future, of course. And these data assimilation procedures, they can optimize the system in various ways. So you can either perturb input forcings and then run an ensemble and see which fits best the observation, or you can perturb model parameters using a multi-model or, let's say, a multi-parameter setup, or you could even also optimize model states. So this is kind of, in a nutshell, how you could think about spatially distributed modeling of snow water current. Now, you can use energy balance models, and it pretty much depends on the accuracy of your input data. If you do have accurate input data or have the good tools to make them accurate by way of post-processing, debiasing, downscaling procedures, then you can arrive at something like this. This is an operational validation of our model that we run over Switzerland at 250-meter resolution on a daily basis. And that's validated against observation from 440 stations available in the mountains, somewhere in Switzerland. And this is all based on numerical weather forecast data, which have issues, as you know, if you look at the cell phone and see what the weather forecast is saying. It's not always accurate, but with some post-processing and debiasing and data assimilation, you get to a performance where you can see model simulation against observation for various elevation bands, starting with high elevation on the left, going to low elevation at the right, if you can't read the fine print, and the black line is the observation, the other are different model configurations. So you can nail this down pretty accurately if you take the effort to work on the input data forcings. But, there's always a but, lateral processes are important for high-resolution simulation. So if you think of a highly complex landscape, you probably want to incorporate lateral redistribution of snow. And to demonstrate just that, this is simulation with the same model, once excluding lateral redistribution processes and one including, which is in the center, that's including, left is omitting those processes. And on the right-hand side, you see the snow distribution in this mountain range based on airborne LiDAR scanning. So that's basically ground truthing. And you can see that there's a big gap between the left, where you just run a physically based snow model, distributed but without lateral exchange process, and the right, the observations. And you can close this gap if you incorporate those processes. But these simulations are difficult, cumbersome, take effort, and they're not often reliable because there's a lot of tuning involved in that. And this tuning usually doesn't really lead to a better transferability to other sites, other years, and so on. So that's a cumbersome business, but sometimes necessary. Obviously, you can also use standard temperature index models. They usually are well working for larger and integrated scales, like lumped spatial scales, larger spatial scales, but they cannot resolve a couple of things, such as aspect-dependent melt rates. They don't see the difference between north and south-facing slopes, usually. They fail in rain and snow situations. Simulations demonstrate just that here. You have a severe rain and snow event that happened in January 2015, and most of the melt actually came from latent heat flux. So condensation of warm air at the snow interface. And that's something that's just generically available in a temperature index model. So you miss the entire melt event if you would have analyzed that by way of a temperature index model. So there are some constraints that you have if you use with these index model types, even though they are very handy because they don't require lots of input data and post-processing of some sort of weather prediction data, something like that. So in essence, there are several options, and here are some consideration when you can use which and when you shouldn't. Now, supporting data sources. Obviously, measuring spatially distributed snow water equivalent is still difficult. You can use whatever point observations, you can use GPR, other technologies, but at the end, to get a grid, you would have to fly, I don't know, some sort of GPR system, which doesn't ever get you probably something like that. I would get at that high resolution. What this is airborne laser scanning of snow depths, not snow water equivalent, see? And then adding simulated snow density to it to make it a SWE product. And that's the closest available data set to a fully distributed SWE observation data set. Here, this is courtesy of the Airborne Snow Observatory in the United States. That's a program that's been established there, but it's mostly unavailable throughout any other countries, I would guess, except for some little test applications here and there. In Norway and Switzerland, there are 1 or 2 data sets, but nothing anywhere close to the operational flights by the Airborne Snow Observatory in the United States. So having something like that would be extremely useful, but is mostly, unfortunately, unavailable, very expensive, obviously. Remotely sensed snow cover data will solve one very important aspect of the whole problem, which is where do we have snow and how much of the snow is melting? But the first question, where do we have snow, can actually be, let's say, fairly simply solved by remote sensing of snow cover. That's, let's say, standard. It's available since many years. Obviously, there's still some shortcomings. So retrieval algorithms still suffer from shortcomings because of terrain shadows. You know, let's say there's half of the valley is in shadow, then it's hard from an optical remote sensing configuration to see whether it's dark gray or not so dark gray. Is that because of snow or because of the debris or whatever? So that's tough. Usually optical remote sensing doesn't see through forest canopy. So do we have snow in 1/3 of Switzerland? We don't know, because 1/3 of Switzerland is forested, and we basically are blind in a large area, fractional area of Switzerland. And cirrus clouds can also provide some difficulties. And well, this here is operational acquisition of Sentinel high resolution snow and ice monitoring data from ESA. And that's 2 consecutive dates. No, it's the 23rd. There was no data on the 24th, and then there was again acquisition on the 25th, and that's all you get. So you have snow-covered fraction in blue to red, and you have no data in forest, which is green, no data in clouds, which is light gray, and no data if there was no acquisition, dark gray. So most of the time, you don't have anything. And in the end of the day, if you run forward models, so operational, you're not really helped if it tells you it's white, it's white, it's white, it's white. That's most of the time the situation in the mountains. So you will only be told that there shouldn't be snow anymore, and that's at the end of the snow season, but you can only fix the snow model when the snow season is still running. So the time of the information that comes in from this data in a forward modeling approach is very, very badly timed, because it basically comes at the end of the season when you no longer need to fix your model, because it's either already broke or you were on point, but it's difficult to use this information in a data assimilation setting. Okay, finally, you can constrain your distributed models, even with non-distributed data, such as station data, so a couple of points here and there. But if you do that wisely, you can use this information, such as in this example, where this is solid precipitation on the input forcing end of the model. And the left is before data assimilation. And you see that obviously the numerical weather prediction somehow overestimated the snow line, and it would only show snowfall at high elevation. And the observation said, oh, hang on, there should be more snow at lower elevation. And that can be fixed even if you don't have gridded information. You can fix this by way of the station, and you see a good match between the points, which is the observation, and the background color in those maps, which is the model simulation of snowfall simulation. So there's some use of this information. So assessing past and predicting future snowmelt. Well, this slide has been on display already, and this is just again to basically say again that simulating these snow in past and future conditions is primarily limited by the availability of forcing data. If you don't have the forcing data in the future, you may only deal with past snow cover. And I kind of color-coded what's required or sufficient for different types of models. So anything that's underlined green is what you will typically need for a physically based model, whereas the air temperature precipitation is just enough and sufficient for running most conceptual models. And then you definitely want to use physically based downscaling methods in order to run physically based models, because otherwise if you use statistical downscaling, you could break physical correlation between your input variables and generate situation, let's say, where you have relative humidity of 90% at the same time it's raining, and you go like, how is that possible? And a physically based model doesn't like that. It will crash maybe or something like this. So you need to be a very, let's say, precise about what you're doing here, whereas statistical methods are absolutely fine when it comes to a temperature index model. So again, you're constrained on the forcing end, mostly because the models can do if you feed them with good input. So using conceptual models beyond calibrated conditions is typically, don't you ever do this. But there's always exceptions to the rule, and data assimilation will provide one. What you see here is simulation for relative snow water current relative to the long-term mean for, 21 years in a series 2004 to 2024. And that's done with temperature index model, but data assimilation takes over for like a calibration on the fly. So every time you advance the model by a time step, you will see what's the observations, and you will try to match up the spatially distributed model with the observation to ensure that the model is on track with the observation. And this is how you can use even simpler conceptual models in the context of longer time series, but that is only working in the past, not in the future, for obvious reasons. But also physically based models are not like the solution to everything. And if you, as I already mentioned, use fabricated data by using simple delta change methods or stuff like this, you may run into problems that are already explained on the previous slides. And this is what it looks like. You have dead pixels, because you may have surface temperature at 0 Kelvin, and you will never melt this again if you run into trouble like this, or you will instantly melt all snow because you have crazy latent or sensible heat fluxes, something like this, because of unphysical conditions. And this will either ultimately delete snow where it's unexpected, like at the high Alps here on the left-hand side, or in the Ticino, where it's warm and sunny, create lots of snow where there shouldn't be any. So these things happen if you don't use the right post-processing or downscaling procedures. So I'm coming to the end, interfacing with hydrological models. I would think that you can use snow models that provides all sorts of things: snow water equivalency, snow cover fraction, snow melt rates, surface water input, precipitation, precipitation split into snowfall, rainfall, whatever you would wish. In the end, my recommendation is to use SWI, providing that you are looking into a one-way coupling at the soil surface. And the reason for that is that you will use the precipitation input that's been used for the snow modeling. You will deal with fractional snow cover in exactly the same way that's been used for the snow model. You will deal with things like runoff through an existing snowpack together with precipitation and the uncovered, unsnow-covered fraction of a grid cell. So it's all solution in one thing. These are examples of different output parameters that you can get from a snow model. And here comes some questions, some input for the discussion that we can go through during the panel discussion. So what, in the end, is the spatial temporal illusion that you would wish to get snow data from us? And that will pretty much determine whether we think temperature index model might be the solution, physically based model. If you don't care about south and north facing SWI input, then why using a physically based model? So that will be one of the things where I would probably appreciate input from you. And how relevant are processes across the snow-soils interface? Because maybe this interface is not the best way to couple models. Maybe, well, we need to model the soil anyway, because there's interaction between soil thermal state and the snow thermal state, so we want to model soil anyway. So the question is, how do we interface in this model in this critical zone? So is that part of the snow model, part of the hydrological model? Should we both do this? So questions over questions. And how to approach catchments where the water budget just doesn't add up. That's commonplace, it happens. So, you have too little precipitation for too much runoff, not even knowing anything about evapotranspiration. What do we do? How do we solve this problem? How do we solve this together? And in the end, how can we collaborate beyond just sharing data sets? So here's my snow data set, do whatever you want to. That's probably not the best approach. And I would be happy if we had some time to discuss this at the end of this plenary. And with this, I would like to close and hand over to Lauren. Thank you so much for your attention.
Thank you very much, Tobias. Yes, let's immediately hand over to Lauren. Thank you.
Okay, hi everybody. Let me start by thanking the conference organizers and for inviting me. I'm really excited to be here. So I've entitled my talk as a follow-up here. So this is Hydrogeology, Mountain Groundwater Under Climate Change. So we sometimes refer to mountains as the world's water towers, and that's because they provide a disproportionately large amount of the world's freshwater resources. So partly because they get more precipitation through the orographic effect, and then through the same effect, you often have arid regions nearby. So they're getting more water, and that water is important to the surrounding area. And then also you have, in certain mountain regions, snow and glaciers that store water. So they help shift water availability from times where there's lots of precipitation into drier times of the year. And that's a really important source of water for many regions as well. And our dependence on mountain regions for water resources is growing. So one study projects that by 2050, 1.4 billion people will depend critically on mountain runoff for their water supply. And we know that mountain water systems are changing. Specifically, a lot of past work has focused on mountain surface water systems. So with, we're seeing reduced snowpacks, glaciers are receding globally, and in response, in many places, we're seeing increasing winter stream flows, decreasing summer or dry season stream flows. And I just got a plot illustrating that from the Bow River in Banff in Canada, so a river draining the Canadian Rockies. So you can see an earlier peak snowmelt flow, you can see a decreased peak and a decreased flow in summer. But one thing that we don't have a good understanding of is how are mountain groundwater systems changing? So maybe 15 or so years ago in the literature, the prevailing thought from a sort of a surface water perspective was that mountain groundwater is not all that important to mountain hydrology. So the idea being not that much water could be stored there or not for very long. But lots of studies have shown that there is an important role of groundwater in mountains for water resources and hydrology. This is a figure from a review paper from a few years ago that I put together, showing the number of papers looking at mountain groundwater through time. So we've seen a lot more papers coming out on this topic and covering different mountain regions as well. And there are some features of mountain groundwater systems that make them a little bit difficult to study. We have steep hydraulic gradients. We often have cold temperatures, sometimes with snow and glaciers. There's a lot of geologic complexity, both in the surficial geology and bedrock geology. And perhaps most important of all, we really lack observation wells in mountains. So our classic tool for learning about groundwater systems, we have very few wells to work with. So I'm going to talk about three main things in this talk. The first is just the role of groundwater in mountain hydrology, what we know and what we don't know. Secondly, I'm going to talk a bit about how we think mountain groundwater will be impacted by climate change from both a modeling and an observational perspective. And then I'm going to finish with some remaining unknowns about cryosphere groundwater interactions in mountains. So what is the role of groundwater in mountain hydrology? So this is our sort of conceptual model. There's a lot going on in this figure, but we've got a high potential for recharge. So we've got certainly recharge from rain, snow melt. We can also get some recharge from glaciers, from mountain lakes and rivers as well. So we've got quite a bit of recharge. And that recharge, one of a few things is going to happen to that recharge. So a lot of it's going to flow towards mountain streams and rivers, either as sort of direct groundwater discharge contributing to base flow, but also through springs. So springs are really common in mountain regions, and they also will contribute to that base flow. And then a smaller proportion of that recharge is going to flow in the subsurface out of the mountains, either to discharge into higher order streams or to become mountain block recharge. So it's going to be an important water resource for those downstream arid regions that are often dependent on groundwater. So from different studies, we know that groundwater is this important contributor to streamflow. So in our review, there were 26 comparable studies we found. There would be more now. Most of them are tracer studies, some are water balance studies, and they show that most commonly sort of in the range of 30 to 70% of water in mountain streams being sourced from groundwater, with lots of variability. And of course, it depends a lot on what time of year you take your measurements. One really quick example from our work is this study about groundwater surface water interactions in the Cordillera Blanca in Peru. So in this study, we used heat tracing and dye tracing to characterize that interaction between the underlying groundwater and a river. And what we found through this experiment was that over a 4-kilometer stretch of the river, just under 30% of that water was coming from groundwater. And a lot of it was upwelling in these flat meadow sections through springs. And, but at the same time, we also found that a lot of the water in the river had just exchanged with the subsurface as well. So about half of the water in the river had gone through this exchange. And that mostly happened in these steeper sections. And all of that to illustrate groundwater is an important contributor to mountain streamflow, and the topography and the geomorphology is also a control on how those interactions happen. So second, how is mountain groundwater responding to climate change? So first, taking a modeling perspective. So this is another study from the Peruvian Andes. And in this study, we were looking at the Chilcas watershed. And the Chilcas watershed is the main water source for a city called Huancayo, with a population of 450,000. And up in the headwaters of the Chilcas watershed, there is the Huaytapiana glaciers that have undergone a lot of recession in recent years. Between 1984 and 2011, there's been a 44% aerial reduction in glacier area there. What we did was used integrated groundwater and surface water modeling to try and understand how this kind of complete integrated system would be changing, where past studies had really focused on surface water glacier processes. So we used a model called GSFlow, which is a mod flow coupled to a surface water model called PRMS. And then we had a simple glacier melt module with a one-way coupling. So we calibrated the model to our field data we collected, and then we applied climate projections to this model between 1961 up to 2100. And these are the main outputs of what we saw there. So each of these lines represents a source of streamflow or streamflow itself. So this dark blue line on the bottom, that is glacier melt, simulated glacier melt, which after a certain point, as the glacier continues to recede, we're getting less and less meltwater contributing to streamflow from that glacier in the simulations until the glacier disappears. In response to that, the light blue line at the top there, that is dry season streamflow. So you can see kind of a decline around where that line says peak water. You can see a decline in this dry season streamflow in response to losing that glacier melt. The yellow line in the middle, by contrast, that is groundwater contribution to streamflow. So that stays sort of more steady relative to the other lines. And it also becomes a larger proportion of streamflow overall. So it's becoming more important as some of those cryosphere features decline. So it has this ability to help buffer water resources. However, you can still see that gradual decline in groundwater discharge there. And in these simulations, that was due to increased evapotranspiration as the temperature increased. The other thing that comes out of that model is you can see or you can simulate some change in the hydrogeological system. If you compare the beginning and end of the 21st century in that model, we saw a mean decrease of 9 meters in hydraulic head or the water table across the model domain. Integrated modeling studies like the one I just mentioned are becoming more abundant. We're seeing them in different mountain regions. And a number of them are pointing to the idea that perhaps we'll see declining groundwater levels, groundwater storage in mountains. But that begs the question, how accurate are these projections? And what changes have we actually observed? As I mentioned, because there's historically not been a lot of wells in mountains, that's a difficult question to answer. But we decided to try. We used data sets from Canada and the US to try and look at this question from an observational point of view. And this is work by my graduate student, Genesee Samways. We compiled all the well data that we could from mountain regions in Canada and the US. We did statistical testing for trends. We looked at a number of explanatory variables as well, so trying to figure out what influences those trends. So we looked at a bunch of climatic variables, physiographic variables, geologic variables, and some human influence variables as well, because of course there's overlaying on climate change signals, there's human actions as well. And then more statistics to try and draw linkages. So in the end, we found 171 wells that fit our filtering criteria. The median length of the records was 33 years. And 54% of those wells showed statistically significant trends, either positive or negative. And of the significant trends, 69% were negative, so declining groundwater levels or groundwater hydraulic head. And 31% were positive. Another thing we saw in the data was that some wells show inter-annual trends clearly, others show intra-annual trends more clearly. So for example, this plot on the left from Santa Fe, New Mexico, groundwater level is fairly steady throughout the year, and year over year is declining. So blue lines are far in the past, red lines are more recent. By contrast, the well in Kamloops, British Columbia, has, it doesn't have a strong inter-annual trend year over year, but you can really see how the shape of the hydrograph has changed. So the blue lines here being from the 60s and 70s, with month, of course, on the x-axis there. So there used to be quite a distinct spring snowmelt recharge event in May and June that's diminished quite a bit in recent years. So here's a map of where we saw those trends in Canada and the US. The brown area is mountain regions, as delineated by other people. And so there's a lot of scatter, and this was a messy data set with, you could have increasing trends, decreasing trends within some area. But we did our best to kind of pull out what could be influences on these trends. And we found, in terms of climatic factors, so warmer and warming, drier and drying locations were more likely to see negative trends in groundwater. We also found that in terms of physiographic factors, elevation was quite key. So the higher elevation, which often went with, of course, colder temperatures, those tended to be more likely to see an increasing groundwater level trend. And then in terms of geologic factors, the most striking one was the contrast between sedimentary and crystalline aquifers, where sedimentary aquifers were much more likely to see decline in groundwater levels than the crystalline aquifers, which on average actually had positive trends. We didn't find strong associations with our human impact index, which isn't to say that some of these wells are not influenced by pumping and land use. They certainly are, but that particular predictor didn't show a strong relationship. So to sum up this section, mountain groundwater response to climate change is part of a system of complex interactions. And those impacts are mediated, so there's certainly direct impacts, but they're also mediated through the ecosystem, the cryosphere, human actions as well. And there's lots of unknowns in this system for sure, but one I'm going to highlight to finish off is this red question mark here, the interaction, so interactions between the cryosphere and groundwater system in mountains. So this was the topic of a perspective piece that came out recently where we brought together people from different regions who were interested in these interactions to kind of have discussions, and we did write this perspective piece about it. And what I think some of the main things that came out were that our understanding of these interactions are certainly still evolving. Some of the main questions we were looking at was how much does snow and glacier melt contribute to groundwater recharge in mountains? We found that in terms of snow, there's much more literature, many more studies on how important snowmelt is for groundwater recharge in mountains. That is established in many places. Lots of remaining questions, but there are more studies on that relative to the question of how much does glacier melt contribute to groundwater in mountains. And that's a particularly pressing question given global glacier recession. So one pathway is subglacial recharge, but also you can have recharge through glacial creeks. And then on larger scales, how much is it possible that glacier melt recharge is important in terms of mountain block recharge? Also, if you have a glacier-fed river draining the mountains, is that glacier melt contributing to mountain front recharge as well? And then there's a question of scale. Do these interactions only matter if you're looking at headwater basins, or do they have impacts at larger scales? And what are the implications for water supply of those interactions as we see cryosphere decline in the mountains? So this is a graphic showing a bunch of research and applied questions across scales. Temporal scale on the x-axis and spatial scale on the y-axis. So just to give a couple of examples here, how vulnerable is a mountain community to climate-driven changes in glacier-fed springs would be one question. Another is, how is groundwater irrigated agriculture affected by reduced meltwater recharge? So some of the questions that remain to be answered. To conclude, my four main takeaways here are first that we know mountain groundwater is an important water resource and an influence on surface water systems. Models suggest groundwater recharge in mountains may be declining with climate change, but the observational study that I presented shows a bit more of a nuanced picture. And we still really lack an understanding of those cryosphere groundwater interactions. So let me just finish by acknowledging the people here that were really key in doing all that work, and there were many more beyond these folks. So thank you very much for listening, and looking forward to the discussion.
Thank you very much indeed, Lauren, and also Tobias for two excellent presentations. So to give you a little break from speaking, I would pose the first question to Tobias, if I may. So as Lauren explained, there's intense interest in the hydrogeological community in projecting or predicting future mountain groundwater trends. You explained that both types of snow models, both physics-based and more statistical, have some key limitations. So what would you propose to be the most promising pathway for making progress in this field? Should most of our emphasis be going into dynamical downscaling methods so that we can apply physics-based models, or do simpler statistical models still have a role to play in future projections?
Yeah, the key limitations that I explained were temperature index models having issues with being applied in conditioned settings and future climate, whereas in physically based we basically have an input data problem because we need physically based between variable consistency when downscaling from whatever resolution you're coming to a scale where this is useful for snow modeling. And here I think that the likely solution is lying in nesting higher resolution simulations in those climate modelings to the resolution that's in the end needed, which is a fully network of simulation from coarse to higher resolution to the final resolution, all in one step, so to speak, in one solution from the climate modeling perspective. I think going down to something like 250, 500 meters is a possibility that's not too far away, and currently there's already regional climate modeling going down the route to these high resolution which are needed, because if you look at 1 square kilometer here in Davos, you basically cover the Weißflur as well as Davos-Dorf down here, all on one grid cell, and it's just not useful to do snow simulation at that coarse scale. So we need to come down to some 100 meters at least. Mm-hmm. And so this is why I'm proposing going higher resolution with those climate models.
Yeah, great. And so continuing on the theme of resolution, I would like to hear from Lauren, at what spatial and temporal resolution do you feel as a mountain hydrogeologist you require, for example, simulated snow water inputs, surface water inputs rather, to inform your work, for example, integrated surface, subsurface models?
Mm-hmm. Yeah, I think it does depend on the application, absolutely. And there are cases where you can and should go, for the high resolution, and then there are cases where you just can't, and maybe that's all right and that works. I think for, we think of, I always talk about wanting more observation wells in mountains. An unfortunate thing is that observation wells are they are kind of a point measurement. So if we, just have a few wells, having a snow water input that is, down to, tens to hundreds of meters is going to probably increase your chances of being able to recreate that. But I think there's still lots of room to sort of push the boundaries of high resolution and small catchments, while also needing to accept lower resolutions in other regions where we just don't have a lot of information.
Thank you. So a question to both of you now. Considering the entire system, so from the cryospheric sciences, the snow, surface water and groundwater, where do you see the greatest opportunities for refinement in our data, understanding and predictive abilities? For example, are the uncertainties in our snow characterization relatively minor compared to our uncertainties regarding the subsurface properties and structures?
Sure. I can comment a little bit. So I think there's a ton of uncertainty. There can be a lot of uncertainty in both. I don't think necessarily that there's so much uncertainty in the subsurface that it makes, the spatial and temporal distribution of recharge, unimportant. Or I think there's, that's a really important. That's the key input, really, right? If you're trying to run a model, is the amount of recharge. So I think that's certainly key. I always, the wells that we do have in mountains tend to be low resolution, so I would be remiss not to say I think we should have more wells in mountains, just to get that sort of basic information. So I definitely see opportunities there, but there's a lot of also really interesting emerging techniques that sort of circumvent maybe the need for wells.
Thanks, Lauren. Do you have some comment on this question, Tobias?
Yeah, I think we would probably be best served if we get away from here's my data set, there's your data set, and let's have some PhD student putting everything together and come with a conclusion that the water balance doesn't add up. So why not bringing people together who have snow data sets? Runoff curves may be biased and they may provoke errors in the water balance, but never the people who do the rating curves come together and do things with us. And if you tell me, oh, we have too much groundwater and runoff, you must provide more snow. There's something, well, I better know in the process of concluding the water balance than just giving a sudden update of my data set. So I think that those water balance projects should be more integrative in terms of let's sit together and see how we solve a problem if there is one, and mostly there are problems, I would guess.
So you're suggesting we need a much stronger collaboration culture. And I think this would, so I think you're really very strongly suggesting that this one-way coupling of you passing your data to a hydrogeologist is not sufficient, and I think this would also then help overcome some of those challenges at these interfaces which you mentioned as well, between the snow and the soil, for example, and maybe also developing more holistic numerical models eventually in future as well. So I think Lauren, what do you feel could be some of the practical barriers towards this more close collaboration, if there are any?
Yeah. So I thought that was, I think we're probably all in agreement that, real collaboration where we're working on teams together is the best case scenario, but there are all these practical things. So as an early career researcher, I sometimes look at people with these amazing research sites where they've got, many people working on the same problem together. And so there's just, there's all sorts of challenges around funding and personnel, and also kind of proximity to those people. Switzerland seems like just the amazing best place to do that kind of work together, but in other regions there are all sorts of practical difficulties. So just a few things, and also depending on if you're in a country that doesn't have a well-established public monitoring network, you have additional challenges to overcome. So just wanted to acknowledge some of those things.
Excellent. And just one final question before we move on to questions from the audience for Tobias. You showed very clearly the value of the airborne snow observatory data in the United States. What do you think is missing or lacking to obtain such data, not only in the European Alps, but across the rest of the world's mountain regions? Do you think this would be a sensible investment, or is that going a step too far?
Well, it's probably very expensive. So, this is a multi-billion-dollar industry in the United States, and I think we are anywhere here in such a setting. I know that there's efforts going on in Norway where there's hydropower, providing the funding for doing such flights, but normally those are then, commercial, and that's my data, and they're not shared amongst researchers in most cases. So basically, if there's funding, oftentimes the data is basically held to whoever paid the data, which is a big pity. So I definitely see lots of value of that, even if I acknowledge that this is super expensive. But focusing on, let's all agree that is a great place to do research, and then putting the investment into those places, not because I, as a snow researcher, say I want this place, but because we all agree that's a great place to make research because we also have this and that and that and that. That would be cool, and then we could basically focus the available funding on those research areas which are helpful for all of us together.
Excellent, yeah. So there's certainly a role for us as scientists also to engage in the political processes and trying to obtain funding for this kind of very important work. I would now like to invite my colleague Clément to pose 2 or 3 questions which have been posed by the audience members.
Yes, can you hear me? Yes. So we have many questions. I try to merge a few of them. So first for Tobias, the question was about the hydrological models, how groundwater recharge is accounted for in these models, and do you consider that feedback from the hydrological model to the snow model is important? That would require a two-way coupling. That's two questions merged together.
Yes, the first question is easy to answer. I basically leave my expertise at the lower boundary of the snow surface, so I don't even do runoff modeling in most of my work. We collaborate with hydrological modelers, but my expertise is really the snowpack itself. But speaking of what we can learn from one another, in particular what snow researchers can learn from hydrologists and groundwater, still precipitation is like, something that's really hard to come by. So we often have not enough precipitation to explain the snow we have on the ground. And sometimes it's easier to go by runoff data or by groundwater and adding that up and giving us good arguments why we need more snow in the models rather than, somehow, I don't know, picking reasons where we don't have hard evidence. So that could be very useful feedback, constraining precipitation. Yeah.
Thank you. Maybe a question for Lauren. What's causing the increasing trend in about 30 of the mountain observation wells that you've shown?
So why is there an increasing trend?
What are the processes there?
Yeah, great question. So it could be a number of things going on. It could be enhanced episodic recharge is one thing that you see some evidence for in some places where if there's more intense precip events, you're getting this episodic recharge that's increasing. That's a possibility. It could be changing snowmelt dynamics as well. That might be, maybe it's a slower melt and that's increasing levels overall. Like there could be a number of complex changes that are not just causing an increase instead of a decrease. So yeah, maybe episodic recharge is one of the most convincing ideas, but there's not a lot of evidence for that in northern latitudes. There's a fair bit in the tropics, but that's one idea.
Maybe a bit more technical question for Tobias. When using data assimilation, do you update states only or also the model parameters?
Yes, updating states is something that I like to avoid because it typically is contradictory to using physically based approach, and that's what I do most of the time. So you want to avoid manipulating states without having the physical basis for that. For me, it's much better using a perfect model assumption, which basically says you can use your model, you can change the parameters, but you don't touch the inbuilt physics in the model. And that would mean change the input data, change model parameters, perturb them, but don't touch the states once they are modeled already. So that hints in favor of the first two options and not perturbing the states.
We have time for one very short
last
question
yeah. Which is perspectives, and maybe first for Lauren, but it would be interesting to have Tobias' opinion as well. How can we work toward closing the water balance in data poor environments, such as the mountain system? So.
Yeah, I think one thing is, like the others were mentioning, if you can pool resources to increase your monitoring density, by working together in one spot, that's going to help. Because yeah, I think it's absolutely true that if your water balance is off, it's really easy if you don't have a lot of data to have evapotranspiration that's off by 5%. So then maybe your groundwater is also off by 5%, or it's definitely difficult to have that perfect water balance. So I do think combining resources is definitely one idea. Yeah.
Thank you very much, Lauren. So now just some closing remarks before we wrap up this first plenary session. I would like to say a big thank you, first of all, to Tobias and Lauren for your inputs. We can give them all a very brief round of applause again. I would like to remind you also that using the same QR code, you can also provide some more general feedback or comments on how we could take this discussion forward during the rest of the conference and also afterwards. I would also like to mention that later on this afternoon we will have a focus event on the emerging discipline of mountain cryo-hydrogeology, so very much on this topic, in which there will be lots of opportunity for interactive discussion and activities. This will be in the Schwarzhorn room at 5 p.m. That's R4. And this will also amount to a contribution to the UN-declared International Year of Glaciers Preservation 2025. So that's next year. If you're interested in the topic, I'd invite you to come along. And with that, I would like to close this plenary session. Thank you very much.